Welcome to Chapter 12, Rotational Dynamics, or Rotations of a Rigid Body. By far, it is the longest chapter this semester. It should have been broken into 2 or maybe even 3 chapters, but the book chose to do it as one single chapter. So this will be a long chapter, and it will require basically twice the effort that you spent in the last chapter, or maybe 3 times. So in this chapter, you will learn and understand and apply the physics of rotations. By the end of this chapter, you will be able to explain the meaning and usefulness of the concept of center of mass. You will be able to calculate the center of mass for a given system. You will apply the center of mass concept in 2 and 3 dimensions. You will calculate the velocity and acceleration of the center of mass. You will be able to describe the physical meaning of rotational variables as applied to fixed axis rotation. You will be able to describe the differences between rotational and translational kinetic energy. You will be able to define the physical concept of the moment of inertia in terms of mass distribution from the axis or from the rotational axis or the axis of rotation. You'll be able to explain how the moment of inertia of rigid bodies affects their rotational kinetic energy. There is an intimate relation between them, just like how mass was connected to translational kinetic energy, the moment of inertia will be connected to rotational kinetic energy. You will use the conservation of mechanical energy to analyze systems undergoing both rotation and translation. You will be able to calculate the angular velocity of a rotating system when there are energy losses due to non-conservative forces. You will be able to calculate the moment of inertia of a uniformly shaped rigid bodies. It will require some calculus use, namely integration. You will be able to apply the parallel axis theorem to find the moment of inertia about any axis parallel to one that's already known. So once you know the moment of inertia basically about the center of mass, you will be able to use this so-called parallel axis theorem to calculate the moment of inertia about any other axis that's parallel to it. We'll see what that means. You will be able to calculate the moment of inertia for compound objects. You will be able to describe the magnitude of a torque, or how the magnitude of a torque depends on the magnitude of the lever arm and the angle the force vector makes with the lever arm. You will determine the sign, whether it's positive or negative, of torque using the right-hand rule, which really is what's called cross product of vectors. We'll see in a moment. You will be able to calculate individual torques about a common axis and sum them to find the net torque. You will calculate, after you calculate the net torque, you will be able to apply that to systems about a fixed axis to find the angular acceleration of that system. Okay? You will be able to explain how changes to the moment of inertia of a rotating system affects the angular acceleration with a fixed applied torque. Okay? You will be able to use the work energy theorem to analyze rotation to find work done, or to find the work done on a system when it is rotated about a fixed axis for a finite angular displacement. And then you will use those concepts to solve problems for the angular velocity of a rigid body using this work energy theorem. Okay. You will be able to find the power delivered to a rotating rigid body given the applied torque and angular velocity, just like how we did with forces. We were able to calculate power. Now you're spinning something or rotating it. How much power are you delivering to it? How much energy per unit of time are you putting in? You will be able to summarize the rotational variables and equations and relate them to their translational counterparts. So you got rotational and linear motion. You'll be able to rotate those two. You will describe the physics of rolling motion without slipping. You will be able to explain how linear variables are related to angular variables for the case of rolling motion without slipping. Okay. You will be able to find the linear and angular accelerations in rolling motion with and without slipping. You will be able to calculate the static friction force associated with rolling motion without slipping, because if you roll without slipping, it means there is some static friction there to be able to allow that. Okay. You will use energy conservation to analyze rolling motion. You will be able to describe the vector nature of angular momentum, just how we had linear momentum, now we will have angular momentum. You will be able to calculate the total angular momentum and torque about a designated origin of a system of particles. You will be able to calculate the angular momentum of a rigid body rotating about a fixed axis. You will be able to calculate the torque on a rigid body rotating about a fixed axis. You will use the conservation of angular momentum in the analysis of objects that change their rotation rate. You will apply conservation of angular momentum to determine the angular velocity of a rotating system in which the moment of inertia is changing. Just like how we had conservation of linear momentum, we will have the concept of conservation of angular momentum, and we will know when it's conserved and not. You will be able to explain how the rotational kinetic energy changes when a system undergoes changes in both moment of inertia and angular velocity. You will be able to describe the physical processes underlying the phenomenon of precession. This is actually an optional topic, but I will go over it. You will calculate the precessional angular velocity of a gyroscope. Again, this is one of those optional topics, but I will go over it. You will identify the physical conditions for static equilibrium now. So after rotating and everything, now what does it take to have something stay in static equilibrium? You will be able to, of course, draw the free body diagram of a rigid body acted on by forces. You will explain how the conditions for equilibrium allow us to solve statics problems. You will identify and analyze static equilibrium situations. You will set up free body diagram for an extended object in static equilibrium. You will set up and solve static equilibrium conditions for objects in equilibrium in various situations. And we will go over these, usually like a ladder leaning against a wall, and what does it take to keep it there, prevent it from slipping. Okay, as you can see, this is a long chapter, and so let's get to it.